There are occasions when we need to conduct flights to an airport where there are, quite literally, no alternates at all. The most obvious example is an isolated island airport surrounded by ocean with no nearby airfield. The route from Santiago in Chile to Easter Island, a popular tourist destination, is one such example. It is 2,029 nautical miles with no airfield available after crossing the Chilean coast outbound. There are alternates near Santiago shortly after takeoff. Valparaiso is one, for example, but there is absolutely nothing near our destination. In this case, the question is not, what is the nearest diversion, but can we safely fly the route at all with the fuel available? We cannot afford to take the risk of arriving at our destination to find that the weather makes a landing unsafe and that we do not have enough fuel left to go back. We are going to establish the maximum range that we can fly outbound and still return within our safe fuel reserves. This limit is called the point of safe return. Let's look at this idea in more detail. Here is a continent or large landmass. Here is our departure airport with a nearby alternate. And here is our island destination. Let's assume that the aircraft has a total endurance to tanks dry of 11 hours. However, we don't operate down to dry tanks. We'll also assume that from the departure airport direct to the alternate requires half an hour's alternate fuel, and that we need to land at the alternate with 30 minutes final reserve fuel. If we go out and back along the route, we must return to the departure airport with a minimum of 1 hour's fuel. We'll disregard contingency fuel in order to keep the explanation simpler. This means that we have a maximum of 10 hours fuel to use on the outbound and homeward flight. Our question is, how far can we go outbound and still return with 10 hours fuel? Shortly before we get to that point, we make a last check on the weather and also confirm that the runway is not blocked. If the answers are unsatisfactory, we turn back. If everything appears in order, we proceed. But we had better be right, because once we pass beyond the point of safe return, we cannot get back with our safe fuel reserves. Let's assume that our aircraft has a true airspeed of 300 knots. In still air, the time and distance to the point of safe return are obvious. It will be 5 hours out and 5 hours back again. At 300 knots, this will be 1,500 nautical miles. We do not consider the time taken in the turn to be significant. Turning through 180 degrees at rate 1, 3 degrees a second, takes only 1 minute. This is negligible compared with the total flight time. The still air case was easy, but what if there had been a head or tailwind component, as there usually will be? We can develop a general solution, whatever the wind component, by the use of algebra. We will now derive the formula to calculate point of safe return in general terms. We'll call the safe endurance E. Note that this is the safe endurance. It is the fuel to be used during the flight and does not include reserves. If we include fuel to dry tanks, we would call it the total endurance. The outbound ground speed to the point of safe return is called O. And the return ground speed back to the airfield of departure is called H. The unknown quantity which we are trying to find is the time to turn back, which we call T. Clearly, the distance out must be the same as the distance back. And distance is speed times time. So the outbound distance is the outbound speed times the time it takes to get there. If E is the safe endurance and T is the outbound time, the return time must be E minus T. Therefore, the homebound distance is the speed, h, times the distance, E, minus t. Let's multiply these terms out. OT equals EH minus TH. we'll write OT as TO. But we want to isolate T, so let's get both terms containing T on the same side of the equation. We factorise, then divide both sides by O plus H. This gives our equation for T. T equals EH over O plus H. This is the one you must remember. You will not be examined on the derivation. We showed it to you to demonstrate that this equation is based on good logical algebra and is correct. But whether you remember the derivation or not, you must remember the result. Finally, having got the time to the point of safe return, we get the distance by multiplying t, the time, by O, the outbound ground speed. Point of safe return used to be called point of no return, and often still is. You can see why. Up to this point we can return safely, so point of safe return is a good name. But once we pass it, we cannot return. We are committed to going on, so it is also the point of no return. Both names have been used, but possibly point of no return sounds a bit too much like the Bermuda Triangle these days. However, if you see any of the following terms, point of safe return, point of no return, PSR or PNR, they all mean the same thing. However, they are not the same as point of equal time or critical point. Let's remind ourselves of the difference. Point of equal time is a time problem. It is about achieving the shortest time to the nearest alternate. The amount of fuel carried is not a consideration and does not appear in the equation. What is important is the distance between the alternates, and this is an essential entering argument for the calculation. Point of safe return is a fuel problem. The distance between the two airfields makes no difference to the calculation. How far you can go out and come back on a single load of fuel is the same whether the destination is here or here. Clearly, this second situation is much more satisfactory from a practical point of view. It means that you can proceed to the destination, fail to get in, and still get back to the departure airfield. But the distance between the airfields does not affect the calculation of the point of safe return. You can think of point of safe return as a radius of action for a given amount of usable fuel. In fact, the longest route in the world with no destination alternate is Santiago to Easter Island at 5 hours, but the aircraft used, the Boeing 767, has enough fuel to make the journey there and back. The destination is inside the point of safe return. However, that would not be the case for an aircraft with a shorter endurance. Because the formulae for point of safe return and point of equal time are so similar, it is easy to confuse them. However, there are important differences. A point of equal time situation is an emergency, often following an engine failure. The flight may have to be carried out at whatever altitude is safe or can be attained, which may be non-standard for the direction. A point of safe return is not an emergency. It is a regular plan for that route to cover the case of weather being out of limits or the runway being blocked. The procedure may have to be invoked quite often, depending on the frequency of bad weather in the region. Also, the route is flown at normal planned flight levels, including the correct semicircular for the direction. Be sure that, in any exam question, you understand what is being asked. Remember that point of equal time questions often include unnecessary endurance information, and point of safe return questions often include unnecessary distance information. Examiners are like that. Let's now apply the basic point of safe return equation to some numbers and see what the effect of wind is. We'll start with the still air case. We will assume that we have a total endurance of 11 hours, but that we need to keep half an hour for alternate fuel and another half hour for final reserve fuel. Our safe endurance is therefore 10 hours. As before, We'll disregard contingency fuel in order to keep the sums simple. Our true airspeed is 300 knots. Get the basic equation down and then start substituting into it. T equals EH over O plus H. E is 10 hours and H is 300 knots. Put them in. So, 10 times 300 over 600 is 5 hours. This is what logic and common sense tells us must be right for the still air case. 5 hours at 300 knots comes to 1500 nautical miles.